Good evening, everybody. Thank you for coming out tonight. Luckily, the weather turned a little bit nicer this evening. It wasn't pouring rain like all night last night. So welcome to the first Center for Values in Medicine, Science, and Technology lecture for 2012. This is an exciting series that we're halfway through now, roughly, on the topic of science policy and cultural values. And the lecturer you will hear tonight, you'll hear about her in just a moment. But I want to tell you that in February, we have 2 events, discussion forums with local experts. In 2 weeks, we've got one on that's going to be on funding of research and the ethical issues that come along with, for example, military funding of technological research. And towards the end of February, we're going to have another lecture talking about science, policy, and education, which should be very interesting. As many of you may know, there's some controversial issues there, especially in Texas. And then in March, as you'll see in your program, we have Nancy Cartwright coming to speak, who is a fantastic philosopher of science who's trying to figure out how we use evidence, scientific evidence, in policymaking and how it's done and how it could be done better. And then in April 13th and 14th, we're doing a conference, which will be an academic conference, but the public will be welcome to come, about all the same issues, about the interaction between science and policy. So I'm going to introduce the introducer of our speaker. So Fred Grinnell is an affiliated faculty member with the Center for Values. He's also a professor at UT Southwestern Medical Center, and he works not only in biology, but also in the area of philosophy of science. He has a fantastic book, The Everyday Practice of Science, which was a finalist for the recent Royal Society Book Prize for popular writing about science. So please welcome Fred Grinnell to introduce our speaker.
Hello, everyone. So practicing science requires deciding what to do, when to do it, how to do it, and who should pay for it. Some people would argue that these kinds of decisions are matters extrinsic to science. And what about the following question? Should the strength of evidence required to support a scientific discovery somehow depend on the importance of the discovery or the consequences of the discovery being wrong? A half-century ago, Thomas Kuhn shook up establishment views of science with his emphasis on the importance of individual biography and personality in scientific judgment. Like the emperor's new clothes, the idea that science was value-free suddenly evaporated. In its place, key questions arose. What is the proper role of values in science? How should science policy take account of values in science practice? Our speaker this evening, Heather Douglas, has made answering questions about the role of values in science and science policy the focus of her work, epitomized in her 2009 book, Science, Policy, and the Value-Free Ideal, published by University of Pittsburgh Press. Heather is particularly interested in the relationship between citizens and experts in democracies and the norms that should govern the weighing of complex sets of evidence for use in policy making. Her work on these topics has been supported by grants from the National Science Foundation. So Heather did her undergraduate work in physics and philosophy at the University of Delaware, graduating in 1991. In 1998, she completed her PhD in the History and Philosophy of Science department at the University of Pittsburgh, and subsequently she became assistant professor of philosophy at the University of Puget Sound. She has held several academic positions since then, culminating in her recent appointment at the University of Waterloo, Ontario, Canada, as the Waterloo Chair in Science and Society in the Department of Philosophy. We're delighted to have Heather here lecturing to us this evening. Please join me in welcoming her to UTD.
So thank you, Fred, for that incredibly gracious introduction. It's a real pleasure to be here as part of the Center's activities. And I think Matt has put together a really spectacular program for you this academic year. And I'm pleased to be a part of it. So, science versus politics, the battle for integrity. How should we think about the relationship between science and politics in contemporary culture? Since 2001, we've seen many books published on the issue of the politicization of science. From Politicizing Science by Goff, published in 2003, Waxman Report, Bending Science, Merchants of Doubt, all with rather bleak assessments of the relationship between science and politics, and in particularly of a potentially pernicious influence of politics on science. And there have been responses, starting with the Data Quality Act of 2000, which was supposed to ensure the quality, objectivity, utility, and integrity of scientific information to be used in public policymaking. And how that actually played out in the next 10 years was less than successful, so that when Obama took hold of the White House and asked for the protection of scientific integrity and for science to be restored to its rightful place, he placed on his science advisor Holdren's shoulders the job of figuring out how to protect scientific integrity. Holden responded with things like, well, we have to make sure we protect scientific integrity. So, not a lot of clarity has been achieved on the politicization of science. And there have been various responses, such as we have to keep science and politics separate, or perhaps defend the value-free ideal for science, or perhaps maintain the rightful place of science. But what these are actually supposed to mean and whether or not they're a good idea are rarely examined beyond the rhetoric. So, the first place to start is to note that politics and science can often have a useful relationship to each other rather than just a destructive one. Not every political influence is politicizing in that pernicious sense of science. For example, the need for oversight of human subject research is certainly a valid and legitimate influence of politics on science. The fact that we think we need to have reviews and regulations on the use of human subjects in research is an important political influence on science, but not one we would consider pernicious. Nor would we consider pernicious the use of funding incentives to direct scientists' efforts to particular areas, such as the recent nanotech initiative that really sort of tries to get scientists on board with doing certain projects as a pernicious politicizing. But clearly some political influences are dangerous. We think of the classic example of Lysenko in the former Soviet Union, where scientists who spoke out against Lysenko were censored to the point of being sent to the gulag to their deaths in some cases. Keeping scientists from saying what they really think, or suppressing results that are politically inconvenient, or directing investigation away from things that the public might need to know. This is happening currently, or being overcome currently in some cases, with new technologies like fracking. If you're going to assess the impact of fracking on water quality, you would better measure water quality before the fracking starts. Right? And if you haven't done that, you're not going to be able to tell. So these raise certain questions. When is science politicized, and when is it not? Not every political influence politicizes science. When does politics, or when do politics threaten scientific integrity in a way that we might worry about? In order to answer that question, you have to know what scientific integrity actually is. And that's going to lead us to questions about what role, if any, value should play in scientific research. And finally, does the protection of scientific integrity actually fully protect science from politicization? So the argument I want to present tonight goes as follows. I'm going to argue that scientific integrity should be defined as the constraint of values in science to their proper roles. My view is that values actually have a role to play throughout the scientific process. So the value-free ideal will not do. But we can articulate a better ideal for values in science, one that acknowledges science's social responsibility in the face of uncertainty. Having the ideal that I'll lay out for you tonight will enable us as citizens to better and more effectively assess the public expert scientific integrity, because we'll know more precisely what we're looking for. Now here's the depressing news. Even if we define scientific integrity precisely and protect it perfectly, protecting scientific integrity is crucial but not sufficient to protect science from politicization. There are still ways to politicize science even in the face of perfectly protected integrity. So that's where we're going tonight. Values in science first. So first I want to unpack the structure of values in science for you. When are values acceptable? At what point in the scientific process? Which values are we talking about anyway? And in what kinds of roles in the reasoning process? The first thing to note is that before you can even begin this process, you have to realize why it is you value science. Why do you care about the practice of doing science? Why do we do it? What is special about this particular approach to knowing that we spend billions of dollars pursuing it each year and hold scientists in such generally high esteem? And one, I think, answer to this that clarifies things is that science is very effective at generating explanations of available evidence and using those explanations then to generate further tests, which then generate additional evidence, which then generate additional refinements in the explanations. It's an interaction between explanations and the implications and predictions that follow from it. This has been a highly successful endeavor historically, as any glance at the history of science will tell us. It's also ampliative. It's an inference mode. Science philosophers call this ampliative. The conclusions are often bigger than the evidence on which it is based. And this means that the results are never completely certain. We do not have Cartesian certainty about science because it is ampliative. You can always be critical of any held belief in science, although it can be more difficult to be critical of some beliefs than others. New evidence could overturn what we now think in any area. And in fact, many scientists think that in some areas we're on the verge of exactly that kind of major revolution. This makes science endemically uncertain, but it's also the source of why it is our most robust form of knowledge, because it's always held up to the possibility of critical scrutiny, to being overturned by evidence, is the very reason why it should be thought to be so reliable. So that's why we value science. And if we think of the values that are constitutive of science in this sense, there are certain things that we need to have in any scientific claim in order to even be able to assess it against the evidence. So for example, we need science to be internally consistent, because without this, we can't actually even derive implications in a coherent way. If evidence is to matter at all, the scientific views must be internally consistent. We also need to have theories that are empirically adequate or predictively competent. You don't hold views that are clearly disconfirmed by available evidence with no countervailing alternative explanations. These are the minimum requirements of empiricism, the minimum needs for empirical adequacy. Because science cares about evidence, this is the things we have to hold in mind as being basic in science. So we should demand that every scientific claim meet these baseline criteria. For doing so captures what we value about science, that it is corrigible and thus robust, that it is empirical and thus reliable. There are other values, though, and these are the ones that we mostly worry about when we talk about science and society, and that philosophers talk about when they talk about the role of values in science. They can be divided up in any number of ways, but here's a reasonable schematic. You have cognitive values. These are values that are often thought to be internal to science, although I think a more complicated view is needed. Things like scope, simplicity, unification, and explanatory power. These are nice things to have in one's scientific theories. Generally, it's better to have, if you're a scientist, a theory that has broad scope or is simple or unifies phenomena in a nice way. But we should keep in mind that having these characteristics is usually not truth indicative. Instead, they're good hedges against uncertainty because these theories reflecting them are often productive of further empirical tests and thus of gathering new evidence and of further refinements. They can also be good assurance against ad hocery when applied to the evidence theory relations, but this is not their actual usual interpretation in the literature, and so I'm going to set that aside here. That's actually a different talk. So let me set that aside. Then we come to social values and ethical values, and these are often the values that raise concerns about the roles of values in science. But what I want to argue tonight is that making distinctions in the kinds among these values, of trying to divide them up into the right category and the wrong category for role of value, for their role in science, is the wrong question to ask. That instead of the kind of value, that we should think about the role that they play. And there are two roles for values in science generally. There's a direct role, this is the problematic role, where the values are the reason in themselves, providing a sufficient reason to do something. So for example, because I wanted to come to the University of Texas at Dallas and give a talk, that was the reason that I got on the plane. The value was a sufficient reason in itself for me to do something. And the choice I made was made because of the value. So that's the general way in which we think about values in our daily lives. We pick things, we do things because of something that we value. But the indirect role is very important in science. Here, values are used to assess the sufficiency of evidence, whether the consequences of error are actually tolerable in the case that we're looking at. So here, the value plays this kind of role. If I am wrong about a particular claim, there'll be some result, and this result would be terrible. So the value is about the consequences of error rather than about the issue that we're actually examining. And because of the consequences of error, I might actually demand more information for proceeding in one case rather than another. Think, for example, of the case of a misplaced suitcase. If you were in a classroom where you know an absent-minded colleague had left it, you might just think, oh, that's probably so-and-so's suitcase. I'll just run down and see if they left it there. Compare that with a case where the consequences of error are usually pretty small, and it doesn't seem like there's too much uncertainty about it, so it seems tolerable. In a different case, think of a left suitcase in the middle of a busy train station. Much more worrisome. Are you going to take a chance that it might just be someone who absent-mindedly left it? Probably not. You'll probably call a security guard, notify them, because the consequences of error seem much more severe in that case. And the uncertainty also seems higher. So we're going to demand more evidence before taking a certain course of action in one case rather than another. Now notice that more evidence and less uncertainty diminishes the importance of this role. The values are not reasons in themselves for a choice. It's this role that I'm going to argue is pervasive and crucial in science. So in order to demonstrate the importance of the distinction between these two roles and persuade you of this view, I'm going to go through an admittedly simplified view of the scientific process, going through these 5 steps of the scientific research process and examining when is a certain role for the values legitimate and when is it not. And this will lead us to understand what scientific integrity is. So first, choosing a research question, the start of any scientist's endeavors. Which project should a scientist pursue? There are all kinds of interests that go into this decision. Disciplinary interests, questions that one might learn from one's graduate student advisors or postdoc mentors. Personal ethical concerns. Some scientists study, for example, the migration path of whales because they care about whales and they want to try to steer shipping lanes away from the migration paths. Or funding opportunities, which try to direct scientists towards certain societal concerns. So these are all perfectly legitimate ways in which values can actually direct the choices that scientists make in choosing a research question. A direct role for values here is fine, and no one disputes that. No one actually, in all the articulations of the value-free ideal in the 20th century, ever said that scientists should not consider social ethical values in deciding which research projects to pursue. It was certainly a choice that they could make. Now, the distribution of effort across the scientific community might be of concern, but for the individual scientist, a direct role of values here is fine. Things get a little more complicated, though, when we consider selecting the particular methodology you're going to use to pursue the project in detail. Certainly here, ethical values can be good reasons to not do or to do certain work in the direct role. For example, because we care about the autonomy of human subjects, I don't get to round you up and inject you with things to see what happens without your informed consent. It might produce brilliant data, but that's not a sufficient reason to do it. And indeed, we don't think the value of the knowledge that we would gain is sufficient to violate this deeply held ethical belief. So when the very pursuit of science raises moral or ethical issues, a direct role for values is actually perfectly acceptable. But certain other kinds of direct roles can be more worrisome. So some scientists have jerry-rigged the scientific process and selected particular predetermined particular methodologies that will almost invariably produce a predetermined result because they want to get a particular answer. So for example, there were scientists studying endocrine disruption in rats, and they picked a rat model that had almost no sensitivity to estrogen. Well, this is clearly a terrible rat model if you want to test whether or not a particular chemical has estrogenic effects, to pick an animal that will almost certainly show no effects no matter what you throw at it. So a study, we think, should at least have the possibility of defying the scientist's expectations, and indeed this should be one of the things that studies are calibrated for. So when looking at selecting a methodology, it's clear that there are some worries. A direct rule for values can be okay, but not always. And this is a problem for thinking about methodological choices, that some philosophers have suggested looking at things like methodological conventions for. That this is one reason why most sciences, although this too varies across the science, have a p equal 0.05 at least, or no higher than that, I should say, to meet the standard for statistical significance. But that too can vary across disciplines. I've seen everything from 0.1 to 0.003 be a standard in science. So another possible solution is to actually critique and visibly sanction, maybe hand out scientific raspberries for deliberately weak science, like the endocrine disruptor test on rats with exceptionally low estrogen sensitivity. Ultimately, though, this comes down to the integrity of the scientist, that a study's methodology has to reflect the core value of science, its ability to discover that which we do not yet know. So scientists have to keep this in mind when they're developing their methodological choices. But let's keep going to the very heart of science. So you've chosen your research project as a scientist, you've chosen your particular methodology, and you're making sure it's a genuine test. Now you have data. Well, hopefully, when you're looking at the results, it's an easy decision of what to record. That it's just clear what you should write down in your lab notebook. But that doesn't always happen. Sometimes data can be ambiguous. And you might wonder whether or not the run was any good, should it be recorded, or what to actually write down for a particular result. And what's crucial, in my view, is that a direct role for values here is clearly not acceptable. You do not get to write down whatever you want because that's the result you wanted. That's the really crucial moment of scientific integrity, that values cannot and should not serve as a reason to see evidence a certain way, which apparently was what Mark Hauser was doing at MIT, was writing down what he wanted to see about what the monkeys were doing in his tests, rather than what they were actually doing. But an indirect role here, I think, is acceptable and needed. So how does that work? So if we think about that choice where you have to actually write down something and you're not quite sure exactly what that evidence sitting in front of you says, how do you make that choice about what to write down? When making any empirical claim, how strong does the evidence in front of you have to be before you characterize it a certain way? There's clearly risk to getting it wrong. If you make the claim and it proves that you are making perhaps an incorrect claim, there are certain consequences. And if you don't make the claim, but you should have, there are clearly consequences. There's no easy out here. So which consequence of error is worse, a false positive or false negative? And that's true even if you decide just to throw it all together, because then you're losing data, potentially. So there are problems on all sides. Values are relevant in their indirect role here, assessing whether one is sure enough about one's characterization of the data. And I have an apparently classic example of this in a 2000 paper of mine where I look at the evaluations by the same scientists of a set of rat liver slides. Same slides, and depending on which scientist is looking at them, different levels of malignant and benign tumors are found in them. Because some scientists are much more worried about overlooking any potential case of cancer, and some scientists are worried about potentially overcharacterizing the malignant potential in the tumors. I look at the slides, I can't see anything. It's just a bunch of cells, right? So clearly expertise is needed, but values are involved in the assessment. If you can reduce the uncertainty, that's always great. But science can often be really messy in practice, and sometimes that just isn't an option. Like we could have redone the study with the rat liver slides, but it would have cost $3 to $5 million to do so, and no one was willing to cough up the money. Same kind of situation results in the next stage of science, deciding upon results. This is where you've already collected your data. Now it's sitting in front of you. How should you interpret it? What should you make of the data that you've collected? Which claims are supported by the data? And here, again, values should not serve as reasons in themselves to make a scientific claim. The direct role for values is not acceptable. Even if it might turn out to make either a simpler theory or a more beautiful theory or a more politically advantageous theory, that's not an acceptable role for values in the reasoning. The values cannot be evidence in themselves. But values can help assess whether one has sufficient evidence to make a claim. So here we have the indirect role. And a more probably common example of thinking about this is suppose you're a meteorologist, you're looking at the data, and you have to figure out whether or not to issue a hurricane warning. Again, there are risks of making the claim on all sides. There is uncertainty, and you'll probably get beaten up for it anyway. But should you maybe make the warning a little bit earlier and maybe for a broader area, maybe with a higher confidence because you want to make sure people are evacuated? Or do you want to make sure that you don't have too many people trying to evacuate unnecessarily and getting caught in traffic jams and potentially additional accidents? People could die on both sides in this case. And so depending on how you weigh the risks of error, weighing the consequences of making a misstatement, you might make one claim over another, and this is often why meteorologists disagree slightly in things. All right, then back to the final stage, applying the results. You have your interpretation, you've decided what is an acceptable claim to make. To what use should we put the results? Here again, a direct role for values is fine. So we might decide to develop a new technology. This would be similar to selecting a research program or back to the start. Or we might decide to use the knowledge to do something in particular, for example, to protect a species or hunt a species. And again, a direct role for values is fine. The values can help direct us in what we should do. So looking over the scientific process, we see the following shape. An indirect role is fine throughout. But in the first stage, a direct role is fine. In the second stage, things get a little tricky. A direct role can be okay, but there are those caveats about protecting the methodological integrity of science and making sure that the tests are actually genuine tests that could overturn current beliefs. When you get to the middle parts, the 3 and 4, indirect role only, no direct role for values in science. And then we get to the 5th part, the direct role comes back onto the table. Now you might be thinking, oh no, this is a catastrophe. Do we really need values throughout the scientific process? Do we have to let them in, even to the heart of it? And I would argue that we need some reason for the sufficiency assessment. And there are no definitive standards. Across science, there are different claims that are made and different ideas of what counts as sufficient evidence, and that this is actually a good thing, given the potential consequences of error, and given that science is in such an authoritative position in society, and that scientists very often should reasonably expect that people, by and large, take their claims seriously and potentially act on them. You might think that the cognitive values such as simplicity, explanatory power, scope, and fecundity could perhaps fill that gap for us, but remember that they don't actually reduce immediate uncertainty. Just because a claim has more scope doesn't mean it's more likely to be true. They might produce uncertainty in the long run, but it's the short term that we really care about when we're making policy decisions. So scientists have a moral responsibility to consider the consequences of error in their work, partly because we all do, have to consider the potential consequence of error in all our work. And scientists have no exemption from that. But the key thing is that values are constrained to act only through uncertainty, through the indirect role, at the internal stages of science. So values in science? Yes, absolutely. Social and ethical values, along with cognitive values, are perfectly acceptable as reasons for a choice in the direct role, in the decision to pursue science, in the decision of which projects to pursue, in the decision of which methods to use, partly, in the decision of how to use that knowledge at the end of the day, but values have to be constrained to the indirect role when deciding about some details of your method, when deciding how to characterize data, and when deciding how to interpret results. If science is to be able to tell us things we need to know but may not like, which is, I think, a crucial point of having science functioning in our society, values cannot act as reasons for the internal choices of science. And so the value-free ideal should be replaced with this horribly named, but if you come up with a better one, please let me know, the value-constrained ideal. All right, so what does this mean for scientific integrity and for our practices around scientific integrity? Given this view, what scientific integrity is, first, circumscribing scientific integrity to be a quality of individual scientists. That's what I'm really concerned about here, and their reasoning, and thus the particular results and claims that they present. Scientific integrity is the maintenance of the proper roles for values in science throughout the process. The values should not be reasons in themselves for choices when interpreting data and results. They should not direct methodological choices to predetermine outcomes, but they're needed to assess the significance of uncertainty. So scientific integrity rests on the value of science itself. That's the reason why I think the structure of values in science looks the way it does. And so that is quite convenient for me philosophically because I've got a definition of scientific integrity that rests on the value of science. And so it makes a nice, coherent story. Now that's nice philosophically, but what about practice? We need to know what violates scientific integrity. When can we say someone is acting without integrity? Like our monkeys up there, clearly, avoiding things. Certainly the fabrication or falsification of evidence is a failure of integrity, because there you're actually writing down what you wish was the case rather than what actually is the case in your data. Ignoring evidence or cherry-picking evidence amounts to the same thing. You're again constructing the final interpretation or claim so it falls in line with a particular predetermined belief rather than allowing the nature of the evidence to speak more clearly. Certainly deceptive research that has no possibility for real discovery, that is actually just generating astroturf evidence, if you will, that just has the appearance of actual scientific research without actually being scientific research, violates scientific integrity. But so too does the failure to consider criticisms of your own work, which would force you to reconsider perhaps the basis of your claims. Note that all these violations involve values in an improper role in science, a holding on to a view in the face of evidence or criticism that should cause adjustment of that view. As such, they corrode the reason we value science. Now, if you take this view of scientific integrity on board, one of the nice results of it is it allows us to parse the responsible conduct of research in a much clearer way than is currently done in the teaching of research ethics. Currently, oftentimes you get a list of 15 to 20 virtues or issues that scientists have to think about all at once. So for example, the Singapore Statement on Scientific Integrity says, well, the first thing is integrity is important. That's the first point. And then there are like 20 other points that scientists are all supposed to think about. This, I think, is a mistake in helping to guide scientists in the responsible cognitive research. So instead of just a jumble of different virtues, you can divide up the areas of concern to 3 core areas. The first being the one we've been talking about, scientific integrity, avoiding falsification, fabrication of evidence, keeping values to the proper role when doing science, and a full consideration of available evidence. But in addition to that one, there are 2 equally important areas for the practice of science. One involves the communal epistemic practice of science, and here we raise issues of how to mentor our graduate students, how to do peer review of our colleagues, how to proceed with responsible authorship practices, and how to report when others fail to meet their responsibilities, particularly with respect to the first issue. These are crucial practices for keeping the robustness of scientific discovery going and for considering the reliability of science as a whole. And then there are the societal obligations of science, which are no less important. And it's here that we arise the ethical guidelines for human subjects, for animal subjects, and the consideration of social impacts of research. So this helps organize the conceptual terrain rather than having 20 different things to think about. Scientists only have 3. But you're citizens. You don't have to worry about well, some of you are scientists, but many of you are citizens. And what you need is not how to think about the responsible cognitive research. You need to think about those experts, especially those competing experts who give you different claims. And you wonder, who should you trust? Which expert is the more reliable one? So aside from looking at Nobel laureates, like the ones I have listed up there, who are all dead, so that's not much help. Here are some things you can use to assess living scientists who have not yet won a Nobel Prize. First, you want to make sure the expert is actually conducting research within the relevant area of expertise. And by conducting, I don't just mean that they have a PhD, but they're actually doing ongoing publications in the area they're making claims about. This is really crucial because otherwise they could just be saying something that everyone who's in the field knows is obviously problematic, and that they would immediately get critiqued in a peer-reviewed journal article, and the peer reviewers would turn it back and say, look, you're not considering X, Y, and Z, and everybody knows X, Y, and Z. And if they're not engaged in that process, that might raise a red flag. It doesn't mean that they're wrong, but it raises a red flag. So you want experts who are working competently in their area. And then the harder thing to assess, you want to make sure the experts are actually acting with integrity, with who are actually maintaining the proper role for values in science. So it's quite difficult to figure out when someone's actually acting with integrity, but it is easier perhaps to spot the ones who are not acting with integrity. So let's look there. So how do we spot the disingenuous expert? There are several things you can look for. One thing you can do if you actually have a chance to talk to an expert that you might be worried about is ask the expert what evidence might change their mind. And if they say, no evidence would ever change my mind, which apparently some have said, in some cases when I've talked to people who do expert elicitation, you know you have a problem. Because then it's not a matter of evidence. They've just got an ideological commitment to a particular belief. The value is actually directing what they say rather than the evidence. You might also look at debates in the scientific literature. You can also check blogs for this kind of thing, although that can be trickier, to see whether or not someone is pointing out that an expert is holding internally inconsistent views, or views that are clearly refuted by the evidence and just not acknowledging that. That's clearly another red flag. If they're not able to publish in the relevant peer-reviewed literature, another red flag. Or if the expert cherry picks the evidence, so that you know that there's a criticism that's been made that they're not considering something that's in the empirical record or in the published record, and they just don't acknowledge it. And this actually is really something that can be really well tracked on blogs. Now, the hard thing for the average citizen is that for a lot of these things, it's not something you can see in one instance. A lack of integrity is generally discovered in a pattern of argumentation and behavior, rather than a particular instance. So this is something that's actually more suited to, say, a student who's doing a project in a particular area, and they can track an argument over time or a piece of literature. It's something that I have done with the case of S. Fred Singer, who's unfortunately fails the integrity test. So, oh, this is falling out. So, S. Fred Singer, let's do this case. So you see the graph of global mean temperature from 1880 to over 2000. And you might notice that between 1940 and around 1970, temperatures actually appeared to decline a bit. Maybe hold steady, but decline a bit. And this is curious because that period was actually a period of incredible ramping up of greenhouse gas emissions. So it was a huge period of industrial expansion. And you would think if human greenhouse gas emissions were causing global climate change, a warming of the climate, that they would show up in that period. And this was a problem for the anthropogenic theory of climate change before 1990, a genuine sort of empirical worry. But in the late 80s and into early 1990s, scientists began to think about something called aerosols, which are particulates like dust and sulfates that actually get thrown up in the atmosphere along with burning high sulfur coal, just incidentally, and wash out of the atmosphere fairly soon. It usually takes about a year, maybe two, to wash out a substantial increase of aerosols in the atmosphere. And one of the things that happened was in the 1970s, we discovered acid rain, and we put scrubbers on a lot of smokestacks. So this decreased the aerosols in the atmosphere quite dramatically. So one of the things that scientists did is they included aerosols in their modeling, and they found this accounted quite well for the decline of temperature and then its subsequent rise. And they were able to test this claim against the eruption of Mount Pinatubo in 1991. A volcano spews a huge amount of aerosols in the atmosphere, lots of particulates, lots of sulfur dioxide, lots of sulfates, and it gets washed out every year, and they used their models to predict how temperature would actually decline a bit that year and then rise the subsequent year. And it turns out the predictions matched beautifully with the empirical record. So by 1995, the aerosols had been hypothesized and tested as the cause of that temporary global cooling and was sort of an established phenomena in the literature. Nevertheless, Singer continued to use this graph as an indicator of the failure of the anthropogenic climate change theory and the particular decline well past 1995, despite the incredible prevalence of this clear empirical rebuttal of the basis of his claim. So he just, and it was published in Science and Scientific American, and there were all these articles about it, so it wasn't like he could have missed it. Right? He knew it was out there, and he just refused to talk about it. So this is clearly a failure of integrity. You have to actually respond. There could have been responses. There are things that maybe he could have raised, which then could have led to further testing and predictions and modeling issues. But he didn't. He just said the same thing over and over again. That is a failure of scientific integrity. So what am I saying here? If you want to assess an individual expertise with respect to integrity, it's quite interesting. It may not matter where the expert gets their funding. It may not matter even if they have a conflict of interest. A lot of people have been focusing on disclosure of conflict of interest as a potential way to solve the politicization of science, but it doesn't seem to actually necessarily lead to everything that we care about. A lot of really good experts get money from non-governmental sources. Does that mean that they have nothing interesting to say? No. You can even take money, potentially from ExxonMobil, and be a perfectly legitimate and useful participant in scientific discourse. So what matters is how an expert responds to new evidence, how they conduct their studies, how they respond to the debate of scientific discourse. The integrity of the expert is an assessment of the intellectual behavior of the person in this context. It may ultimately matter to us if we have to make a decision whether the expert shares our values, because perhaps we might agree with them on how they weigh the consequences of error more clearly. So that may matter in a certain way, but it's not an assessment of their integrity. We should keep those things distinct conceptually. So what does this mean for the politicization of science? We've defined scientific integrity, hopefully I've given you some tools to assess it potentially in practice. What does it mean for politicization? Well, it should be clear that violating scientific integrity for political purposes is clearly pernicious politicization. If scientists, either for political gain or as due to political pressure, ignore evidence, fail to respond to criticisms, manufacture doubt, create uncertainty when there really isn't a lot, say things that they say just because they think it will have a particular, potentially even beneficial societal effect, but not on the basis of a fair assessment of evidence, that's a problem. That's a pernicious politicization that we would like to forestall. But here's the bad news. Even if you protect scientific integrity perfectly, it's not sufficient to protect science from politicization. Because remember that values are perfectly fine in directing the selection of research projects. So which projects should be done and which are done are often a product of our societal and political values. And many concerns over the politicization of science are less about science lacking integrity and more about which science actually gets done. And actually, it's kind of split right down the middle, to be honest. But there's a lot about which science actually gets done. So to go back to the selection of research agendas, if we don't research something, we're not going to know about it. And a lot of philosophers of science and science commentators have been noticing that there are really clear examples of under-researched areas. In fact, there's a new field called agnotology, the study of ignorance, which examines these sorts of issues. Why do we not know about certain things? So how come we don't know a lot about certain tropical diseases and how we might either prevent them or cure them? How can we know so much more about heart disease? And how come we know a lot about drugs that control heart disease, but not so much about the kinds of foods or exercise regimes that might really help with heart disease or other diseases? And that's partly because you can't patent broccoli, but you can patent Lipitor. So clearly there are commercialization regimes here at work directing research to some areas and not to others. Or how come we know so much about genetically modified organisms, but so little about how composts or composted manure or other sort of more organic farming practices influence the production of food? How can we know so much less about those? Again, you can't patent compost. So there are clearly key influences on research agendas, scientific training and collaborations. One, the sociocultural background, what kinds of, oh, sorry about the tractor being over, what are the plausible explanations? One of the things we want in science is a sufficient diversity of scientists asking questions and attempting to postulate answers so that all the plausible explanations are fully explored. And this is something that feminist philosophers of science have been really concerned about with respect to research related to gender. And then there's the funding issue, and that really does direct the efforts of scientists in potentially problematic ways. I don't know what that's for. So how might we track the distortions of funding? Are there things we could do? Well, one thing that people have been noticing is that a lot of studies are done, but then they don't end up getting published. So we don't actually know about all the kind of failures in science. And this is particularly true in pharmaceutical research, because if you just keep testing a drug on enough populations, somebody will prove to have a positive effect. Right? If you just keep doing the test enough, statistically, you're going to get a statistically significant result at least 1 out of 20 times if p is 0.05. So how do you solve the file drawer problem? One policy response is to create something called the study registry, where if you're going to do a study, you declare an intention to do so. What you're going to do, which populations, what methodology, and it goes on file at NIH. And then people know, oh, someone did a study, even if no paper ever appears, that there was some study done. So if you have 40 attempted studies and 1 positive one, you know something is fishy. So this might help. And this could also potentially help what's called a publication bias. But a more tricky problem is whether or not alternative explanations or options of research are even being pursued to begin with. So if you only study one cause of a problem or one solution, those are the only ones we actually will know about. So how do we actually get a sufficient diversity of effort among scientists so that we can know the things that we need to know? And here, the decisions are much more fraught. Someone like Sheldon Krimsky has argued that you just have to have sufficient public funding, that you can't let private interests swamp public interest science, as he calls it. But some have argued that it's not even a matter of public funding, that we might need different public funding, that the efforts of scientists tend to still get steered in certain directions, either because of internal disciplinary concerns or because of certain external incentives that might push research a certain way. So how do we make sure that that happens and that we have a sufficient diversity among our scientists so that all the possible explanations that we can think of at least now get fully explored? And here we get to a social level assessment of the functioning of science, where we can look at the field of what might be called social epistemology to ensure that the distribution of scientific effort is as robust as it could be, examining which projects are funded and which are not, which questions are asked and which are not. And is there enough diversity among the scientists so that blind spots get examined and critiqued? Part of this is also about making sure that there enough diversity of sort of background of people are in science so that not just gender, but also ethnic background and class background issues get brought in so that a wide range of questions can be asked. And then we can look at whether or not the debate is healthy in science. Are there is finished work freely published, or are there blocks to it? Are there forums for criticism, and are they working? Are alternative explanations being posed and considered? Are those with less power able to raise concerns? And is there uptake of criticism, both by the scientists and by those who are raising the critiques to begin with? It has to go both ways or it's not going to work. So, in conclusion, how to think about values, science, and politics. For values in science, the place to start is what we value science for. And we value science for its ability to tell us things we don't know about the world, even if the body of scientific knowledge is changeable. And we might find out tomorrow that something we always thought was true isn't anymore, and we're all going to be frustrated when that happens. But that's a good sign, not a bad sign about the nature of science. Values serve many crucial roles within science. They're needed to help decide what science to do and how to do it. They need to help assess the sufficiency of evidence for a particular claim. They do not supplant or play the same role as evidence, however. And they should be constrained to that indirect role when characterizing data and interpreting results. It's absolutely crucial. Because although values are endemic in science, science still has integrity. And that integrity is based ultimately on why we value science. So if we keep that in mind, we can see certain things about politics in science. Certainly, scientists lacking integrity or forced to act without integrity, the abuse of values in science can greatly distort scientific debate and politicize science. We've seen, unfortunately, ample evidence of that in the past few decades. But even if scientific integrity is maintained among individual scientists, what we do and what do not know scientifically is deeply influenced by the distribution of effort among scientists. And this distribution can be distorted by power and money. So careful policy for science and for the social functioning of the scientific community are central to reducing the pernicious politicization of science. Thank you very much.
Okay, so we have time for some questions. I'm going to, we've got a couple people who are going to come around with microphones. So if you have a question, comment, right here.
Thank you. That was very interesting presentation, but I didn't hear you mention peer reviews on scientific work.
Oh.
How would you categorize peer reviews in establishing authenticity?
So, I did mention it really briefly on this slide. And also in assessing the integrity. So when I say the expert is unable to publish in relevant peer-reviewed literature, I'm relying in some sense upon the peer review process for establishing the minimal credibility of claims. Now, the truth is, peer review can be fraught, right? Sometimes scientists get a little quickie, and they don't want to publish something that makes their lives complicated. And so just because something hasn't been peer reviewed doesn't necessarily mean it's not any good. But for the general members of the public, it's going to be a crucial step that it have some kind of peer review done. But it's good to keep in mind that for journals, I mean, it's usually sent out to 3 or 4 reviewers. Right? So it's a fairly small group of people, and they're not establishing the truth of the scientific research. They're just establishing that there are no obvious errors. And they can't even tell if the data has been made up. So Mark Hauser's a great case for me, right? He published a ton of stuff in the peer-reviewed literature coming out of his lab at MIT, but no one knew that he was just making up his data, because you can't tell that from looking at a journal article as a peer reviewer. So peer review is both a useful check, but it's not perfect either in making sure that only good stuff gets in, or in making sure that all good stuff gets in. Oh, okay.
What number of peer reviews I would establish some credibility to the research? I mean, would you have 1, 2, 3, 4, half a dozen? How would you pick those?
So I have, okay, let me back up and make a particular point about peer review. There are certainly 2 structures within peer review that are really, I think, essential for good peer review. One, I really think peer review should be double-blind. I think that's been, I know it's often in science, and even in philosophy in my field, a lot of times you can guess who actually did the research. You can sort of tell by what they're doing. If you might have met them before, you know what they're citing, you know what their argument is. But nevertheless, I've been asked to do both non-blinded and blind peer reviews, and I know I do a better job when it's blind. And I think sociological studies of peer review support that. The other thing that I found really useful as a mechanism within peer review is to share the peer reviews among the peer reviewers after it's all done, as a kind of calibration check against one's peer review process. I know of 2 journals that do this, the American Journal of Epidemiology and Science and Education, and I think it should be more widespread. And I think it's really a valuable service to academics as trying to create an epistemic community to see how we do this collectively. And I found that those to be a really invaluable process. I don't think any particular number of peer reviews is ever Well, now we've got the mark for credibility. Because it's going to depend. Who are your peer reviewers? Do they have sufficient perspective and background on the particular thing they're looking at? And if you get the right peer review, one could do. If you got the wrong peer reviewers, a dozen isn't going to do the trick. So unfortunately, I don't think we could do anything that mechanical with the peer review process, which is why it can't serve as a hard and fast, perfect gate, unfortunately. And yet it's crucial to the practices of science.
Hi, thanks for your talk. Two thoughts. One is, as it relates to sensation, like popular science and like climate change,
Right.
and kind of like there's a necessity to get people to understand and be alarmed in some ways, but then like where do you draw the line as far as like honesty about like what's really like timelines and that kind of thing.
Right.
And also, I just had a thought about like as far as algorithmic approaches to seeing inconsistencies in data as a way of trying to maybe see if there was some, fabrication.
Yeah, okay, so first let me address the issue of what you're sort of asking about is advocacy in science in many ways, I think the first question. And a lot of people have in scientific communities have debated the effective or the proper role for advocacy in science. My own view is that it's really important not to overstate the case so that you get a certain result as a scientist. That is actually the road to huge problems down the line. Because if people get a whiff of the fact that you might have been trying to say something to them to get them to act a certain way, not only have you then used a value in an improper role, like the outcome is the reason why you're saying it. That's really not it violates my view of integrity. But it also doesn't pass the smell test. And people will notice. And now I'm going to say something pretty controversial. I think this happened to Jim Hansen in 1988. I think he went to Congress and actually overstated the case for climate change at the time. And what we ended up with is 20 plus years of debate about how much, whether or not we had certainty about climate change, which is the wrong question. It's not whether or not we have certainty about climate change, it's whether or not we know enough to do something about it. And that's a completely different question and would change the debate quite dramatically. So overstating cases to have a desired effect is clearly the wrong thing to do. That said, I think scientists can be advocates if they're what you might consider an honest advocate. If they're really transparent about the fact that because they're worried about certain consequences if people don't take things seriously, like if we decide on the wrong claim societally, and they're really worried about those things, they can say that and make those value claims openly. And then we can assess that on that basis as citizens. That's part of a robust political discourse. So that, I think, would be quite good. Okay, and the second question was about algorithms to test consistency of data and to plagiarism or fabrication detection. And those can be quite useful, but usually you don't do it until you already have some kind of indication there's something funny. Because it's a lot of work, right? It's not something that's really obvious to do. I mean, obviously, Stephen Jay Gould did a brilliant job on this in The Mismeasure of Man, looking at some of the Cyril Burt studies and earlier stuff. But usually the way fabrication or falsification is found out is because a colleague notices. Someone notices that what you're saying about what's happening in the lab is not what's going into your notebook, or what they're seeing is not the same thing. Or there's a really lovely book called On Fact and Fraud by David Goodstein about cases of fabrication, data falsification and fabrication. And what he argues in that book is the vast majority of cases in science of fabrication and falsification are actually of things, not of the unexpected, like the surprise discovery, because that everyone will be critical of, right? So the fabrication falsification will fall apart really quickly. Fabrication and falsification usually happens when a scientist is sort of desperate to meet those publish and perish deadlines, and they make stuff up that they think will be certainly what will happen anyway. So there's a really great example in that book of a case where the physicists expected the next element, I think it was 118, to be discovered and have certain properties. And so someone claimed to have discovered the element 18 with those certain properties. But it turns out the projections were wrong. So until they actually discovered it and realized that they had sort of miscalculated what the properties would be, no one realized that the person had just totally made up the data. And then once that happened, if it had turned out the right way, they probably would have gotten like the Nobel Prize for discovering the element. But as it was, they were sort of excommunicated from the community of science. So it's a high-risk business, making up data.
Thank you for a lovely talk. I have a question. How would you assign value to pure science? For example, how many millions or billions of dollars is it worth to find the Higgs particle? How many billions is it worth to find the nature of dark energy? How many millions, for example, was it worth to prove Fermat's last theorem? How do you assign values, and how do you assign support to pure science that has no direct social consequences?
Well, thank you for an easy question. So this is an incredibly hard thing to answer. I certainly wouldn't put it at infinity because we have finite resources, right? So we can't say that it is the end-all and be-all of all human endeavors, despite the fact that it sometimes might feel that way. So I think the thing we've been doing so far is not too far off from an appropriate thing to do, which is to assign a certain part of our research budget for those endeavors because they are valuable both intrinsically and for the potential. I mean, the Higgs boson might have some application. Who knows? But that's not why we're doing it, clearly. And to help let the scientific community decide how to divide up those funds. That seems to me the only sensible thing to do. And then to ensure that there's sufficient robustness of the discourse within the community about that division. So you don't want it to get sort of overly dominated by one school or another. I think Lee Smollen's been raising certain concerns about this with respect to string theory, for example, that it's gotten a little too dominated by a particular view and that it's sort of harming the creativity of physics. So those are, I think, about as much as I think I could say, which is far less precise than perhaps what you were hoping for.
Thank you. My name is Owen. I am a sociology major, undergraduate sociology major. And as a scientist, a social scientist, I want to thank you for coming to our campus and enlightening us with your knowledge. Would like to have a clarification or a question, a better explanation, elaboration. On the wellness slides, there was something that you posted. It says the two roles or values in science. If I'm not mistaken, those are the direct role and the indirect role. Will you please, will you please elaborate on that for me? Because I was unable to catch it as I was trying to write down, taking notes.
Yes.
Thank you.
It's an excellent question because this can, for me, it's very clear, right? But I've been thinking this way for about 10 years, so that's not very fair. So in the direct role, the value is sufficient reason in itself for why you do something. So here's a really simple case. You are picking out desserts, and there's chocolate cake and there's carrot cake. And you like carrot cake better. So you pick that one. The value of carrot cake over chocolate cake is the reason why you pick the carrot cake. Values in the direct role. You're a scientist. You really care about, say, the suffering of people in Africa under the scourge of malaria. And for that reason, you decide to work on the genetics of Anopheles, the mosquito that's the carrier, to see if a genetically modified mosquito might cease being a carrier for the parasite that causes malaria. The value serves as the reason for why you're making the choice you're making. That's the direct role. The indirect role, in contrast, is not a reason in itself for the choice. It operates on the margins. So you have evidence in front of you, and you're trying to figure out, is this evidence enough? Are the other reasons, so the evidence is the reason ostensibly for a particular choice, like to make a claim such as my mosquito will actually reduce the scourge of malaria. Do you have enough evidence based on the research you've done so far? And there might be consequences of various kinds of error that you might worry about there. Making a claim prematurely might raise hopes, might divert funding away from things that might be more practical. It might also lead to various sort of unintended but clearly foreseeable consequences you'd like to avoid if your theory proves wrong. On the other hand, waiting too long to make a claim, to sort of make sure the evidence is completely undeniable given the current state of our empirical knowledge, is perhaps waiting too long so that people don't use the technology sooner or use the knowledge sooner to actually reduce the scourge of malaria. So there, the value is operating to see, like, well, is the uncertainty that I still have, given the evidence available, is it acceptable? Or do I need to gather more evidence before I make the claim? Is what I have enough? And so you could always decide that, no, it's not. I'm going to go gather more evidence because the value, even though I might really want to reduce the scourge of malaria, I just don't have enough yet to work with. Does that make more sense?
It does. Thank you.
Fabulous.
One of the most profound values in the academic world is the acquisition of external funding. No, a very serious question. How does the role of external funding, which plays a major role in promotion and tenure and reputation, relate to your concerns about politicization of science?
Well, it's huge. Partly because of the shift in the past 10 years. It used to be in this country that actually the majority of science funding was actually public. That is no longer the case. So at this current time, more science is funded through private sources than than public sources. And so one of the questions we have to ask is this distorting our empirical view of the world because of where the funding is going, the kinds of research it's doing? Because, of course, professors do need to get funding. I mean, it's almost a requirement of being a professor in the sciences these days that you have some form of external funding. It's very, especially at research universities. I mean, liberal arts colleges, you can get away without external funding, but research universities, no. If you're not funded externally, you're out of a job in pretty short order. So, how do we make sure that that there's adequate funding and sufficient competition and not an undue direction pushed on these things? And I don't know what the answers are to that. At this point, all I can do is raise the question, because part of it is, do we want to increase taxes? Do we want to sort of force? One thing we could do, so I mentioned this in my radio interview earlier today, and I actually found out, so a guy, Julian Rice, had this really clever proposal for dealing with the problem of pharmaceutical funding. Right? So a lot of university scientists take pharmaceutical funding to do research on drugs. And where else are they going to get the money to do this? The public funding isn't that robust for it. The pharmaceutical companies have the incentive to fund this research. But if you rely upon money from, say, a particular company, and you're going to want to go back to them because you're going to need to keep funding your lab from them, there's going to be an additional unfortunate and biasing incentive to produce results that the company is going to like. And this is exactly the kind of violation of scientific integrity that I would be really worried about. So one way to avoid this is to demand that if you want your drug approved by the FDA, Julian Rice has suggested that we set up a central agency that is funded by the pharmaceutical industry, not entirely by public funds, funded by the pharmaceutical industry, and that any drug that has to be approved has to have studies supporting it from this agency. And so the pharmaceutical industry would have to funnel their money through an agency that would create like a firewall between themselves and the university researchers, course, it probably would turn into a revolving door firewall, but at any rate, it would be a potential institutional start to give a bit of room so that researchers could potentially come up with be willing to come up with results that the companies wouldn't like, because their direct paymaster is actually an agency whose main concern is the integrity of research as opposed to getting market approval. That's one possibility, and that could potentially be applied to other areas. Any place there's a regulatory approval process, you could sort of potentially create this kind of institutional buffer. No fighting over the microphone.
On ethics, I noticed convoluted paragraphs on technical subjects in newspapers and in advertisements by prominent corporations. The convoluted paragraph, if you read it real fast, it says one thing. If you sit down and study it for 15 minutes, it says something else.
Yes.
You know what I'm talking about?
Yeah, it's that this drug might cause ask your doctor. Right, that paragraph, right?
These convoluted paragraphs are designed to develop public opinion amongst people that don't understand the subject.
Okay, so what's the solution for that? First of all, ignore the convoluted paragraph. Get a second source. And hopefully, this is, I think, the role that science journalists should be playing in our society, is processing this information for us, getting critical perspectives on it, not just a competing expert account, but actually doing critical analysis themselves to see, are there good arguments on both sides, or are there even both sides, or is it really one side and then like a completely crazy view over here that has no basis whatsoever that we should completely ignore. So this is, I think, a role that the media has not been doing well. And it would be really nice if schools of journalism that train people to do science journalism would take seriously some of this critical analysis of science and build that into what is considered good science journalism, as opposed to objectivity as two competing experts, which is clearly not helping us or public debate.
I'm afraid we are running out of time for conversation tonight. I would love to stay here and talk about this all night.
I know you would.
But I think that we better give our speaker a rest. So please join me in thanking Heather Douglas.
It was really fun.